the linearization of a function in multiple variables. So it's the exact same thing as the linearization of a function in one dimension. And if I have a function here, and I want to approximate that function with a straight line, I do so with the derivative. This straight line is equal to the value of the derivative, right? The slope of that straight line at that point times how far away you move away from that point, right? This is exactly a straight line equation. Y is equal to mx plus b. Oh, oops, that's actually just the differential. I need to start at my initial point, right? So this puts me right here at this spot, and then this part of the equation tells me to travel in that direction. Okay, so in multiple dimensions, it's the exact same thing, except instead of traveling along tangent lines, we travel along tangent planes. So we want to find the linearization of this function, x squared minus xy plus 1/2 y squared plus 3 at the point 3, 2. All right, so our function is going to be approximated with a linear function, i.e. the tangent plane. Which is, I give myself an initial value given to me by the function, and then I use the derivative to tell me how I'm going to change. So this function is a function of two variables, x and y. So the partial in the x times the distance traveled in the x, where it's understood where I write f sub x, that partial is a function of x and y. All right, but I can not just travel in the x direction, I can also travel in the y direction. So that tells me how fast I travel in the y direction, right? It's the slope of the function in the y direction. And this tells me how fast or how far I actually do travel in that direction. Right, so it's the exact same thing. Initial point plus gradient vector dotted with a direction. Okay. So let's go through this. The function value we want to approximate. Is it at the 0.43? No, we want to make our approximation using the 0.32 and then use our approximation to evaluate the function at 4,3. Okay. So that means this 3,2 is where we want to start our tangent line. So the function value at 3,2 plus my partial derivative in the x evaluated at that 3,2 times the travel in the x. Actually, we know the x value. 3 plus the partial derivative in the y at that point 3,2 times the travel in the y. All right. When you go through this, you end up at 8 plus 4 times x minus 3 plus 5 times y minus 2. And simplifying, you get that the linearization is equal to 4x minus y minus 2. So the function value at 4,3 is approximately equal to the linearization at 4,3. And that's what this says. That's the whole reason why we travel along the tangent plane. So if I evaluate my linearization, my tangent plane at 4,3, I believe you get an 11. All right, let's see what the actual function value is at 4,3. Right, I mean, I know my function value, so I didn't really have to approximate it. My function value at 4,3 is 11.5. Therefore, the error, which is the difference between the linearization and my function value, right? How far off is my approximation? 0.5. And that's the difference.